Okay, so we're going to talk about the squeeze theorem for a moment, and then we're going to talk about some trig limits. Okay, so the squeeze theorem. It's named the squeeze theorem for a reason. Okay, so if I have a function squeezed in between two other functions, so f of x is squeezed between h of x and g of x. If our outer functions have the same limit as x approaches c, then the function squished in the middle also has that limit.
You want us to write all that?
If you want to summarize it in a different way, you are welcome to. So f is squished between two functions. The two outer functions have the same limit as x approaches c. So the meat of the sandwich, right, the one in the middle, would also have that limit. The outside ones do. To be honest, this is a theorem that is used very, very, very seldom. Okay, you're going to see it once in a blue moon, or maybe once in a full moon. Okay, we'll see it maybe 2 or 3 times throughout the year. So we don't use it often, but it can be very powerful. Okay, so we have two functions, a third function that's in the middle. The outer functions have a limit towards c that's the same, then that middle one, I mean, its only choice is to have that same limit. Okay. So this can be helpful in times where we don't have an algebraic technique to help us. Okay. Okay, we want to find the limit as f of x, or excuse me, as x approaches 0 for x times the sine of 1 over x. Okay, let's look at the graph. Well, first of all, I'll write it like this. What's the problem with plugging in 0? We have a 0 in the denominator, and we have no algebraic strategies to get it out. Okay, so let's graph it and see what it looks like. Okay, so in my graphing calculator, I'm going to make sure that I am in radian mode. Okay, what was it? X sine of 1 over x. Okay, so we could probably, it's kind of hard to tell what's happening there. But can we think of two functions that would sit above and below that graph? A function that would sit above, a function that would sit below. Your clocks are not from I don't know why. Okay. Well, y equals 2 would sit above it, but then we couldn't have something below it that would match up in the middle. Like we want something that comes together right here,
Oh,
right? So we can have that sandwich effect.
do like x squared and negative x squared.
Would that work?
Yeah.
Ooh, I'm not sure, actually. Let's see.
Your word. Do x.
Ooh, absolute value. So,
Oh,
so that's not really working, right? Let's try absolute value. Who said that? Who said absolute value? Nice work. Okay. So, which means what could be on what?
How do you graph absolute value?
So if you go to math and arrow over to numeric, ABS is absolute value. What? Oh, yep, that's the value of X. So what could go below?
Negative.
Negative absolute value of X. Okay? I am so proud of you all. So if that's the case, so we have like this. Why is this just taking so long? This is excellent. Okay, so we have the absolute value of X. There we go. The negative absolute value of X. And I can't remember like really what is, something's happening, right? Well, towards 0, right? What's the limit as X approaches 0 of the absolute value of X? 0. What's the limit as X approaches 0 of negative absolute value of X? 0, okay? So since 1 over X sine of X, that's not X sine of 1 over X is squished in between positive absolute value of X and negative absolute value of X. Since these two have the same limit, then we can conclude that the limit as X approaches 0 of X sine of 1 over X is also 0. Woohoo! Yes, this would be a part of it. To be able to use the squeeze theorem, you need to tell me that you have the function squeezed between the other two, okay? And I would want to see the limits of the outer ones, okay? I mean, this is your final answer, but I would want to see this in your work to know that you use the squeeze theorem. How many of you have a strong bond with trigonometry? Like that was like your favorite part of your calculus, was the trigonometry part. Yeah, it's all good. 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 All right, we're gonna do some trig limits. Okay. Some of you, I don't know if they're being sarcastic or not. Okay. You are always going to start with direct substitution when we're evaluating limits, even if they're trig. Okay? So the limit as x approaches pi over 3 of secant of x. If we use direct substitution, what is the secant? Pi over 3. Is it 2? Was a question. Will somebody answer?
Yes.
Okay, got confirmation. Good.
Is this?
Do you need blank unit circles?
Yeah.
Like, I don't
Yeah, we're done with squeeze theorem. Just for minutes, not forever. You're probably gonna have a homework assignment with it. All right, the limit as x approaches 5 pi over 6 of the tangent of x. Think about it, don't say anything. Write it down. Turn to your neighbor and whisper what you think the answer is. You need a blank, use a circle? Here, all you need is the first quadrant.
I like this. Trying to visualize here. Oh yeah, I just need to know like the pi, like the radians. Like doesn't it go 5 pi over 6 or 5 pi over 6? Okay, but they're both negative. No, it's in this class.
Max, what's your answer?
Negative radical 3 over 7.
I was never going to do that.
Whatever x. You do not get to say you were not good at it. All right. Now, we have some special trig limits. You need to write these down. And you may need to use some trig identities to help you evaluate your limits. Okay? It is possible that you need to rewrite something to help you. Maybe simplify, like if you're getting a 0 in the denominator, you may need to rewrite your trig function so that something can cancel out. Okay? You know that tangent is sine over cosine. You know that secant is 1 over cosine, things like that. Okay? It is possible that you need to use trig identities. Okay? There are also two special trig limits. The limit as x approaches 0 of sine of x over x equals 1. And the limit as x approaches 0 of 1 minus cosine over x equals 0. Write them down. Memorize them so that you can use them. Just FYI, the reciprocal of this one will also be true. You can have x over sine of x, and it'll still equal 1. We can take the reciprocal. I mean, the reciprocal of 1 is 1. Okay. So it doesn't matter which fraction you have. It can be flipped. Okay. Also,
Does that work for number 2?
no, because it equals 0.
Okay.
Because and reciprocating 0
Got it.
doesn't really work. I know, it's sad. When you talked about trig identities back in your pre-calculus class, we talked about how the angle needed to be consistent. Like your angle could be x, your angle could be theta, your angle could be 1500. Okay, it just had to be the same throughout. The same applies to these as well. So if we have this limit right here, I'd write this down because we're going to do this. The limit as x approaches 0 of sine of 2x over 2x. Okay. Since our angle matches the denominator, then we can still apply this theorem and this equals 1. Since our angle matches our denominator, we can still apply this theorem and our limit is 1. You got it, 51?
Yeah.
Okay, so we have 11 minutes, maybe 10 minutes We have 10 minutes, and I have potentially 3 examples. We'll just see how long it takes us. I'm hoping we can get to all 3. Okay? Okay. The limit as x approaches 0 of tangent x over x. Why are you giving us a tangent? We didn't talk about tangent in our special limits. Just a tricky question for you. Thank you, Nancy. Okay. I've been hammering since yesterday. We always start with direct substitution. What happens when we direct substitute? 0 over 0. Not ideal, but probably means we can do some finagling. Okay? What's our option here? Make it not tangent. What could we make it? We could make it sine over cosine. Right? Which really just means we have sine of x over x times cosine of x. Okay? Well, that's cool. We have sine of x over x, don't we? And our limit is approaching 0. So what's the limit as x approaches 0 of sine of x over x? Okay. Ethan, what's your question?
Did you do that wrong? Is sine of x supposed to go to the denominator?
It is not, because when we divide, it's the same thing as multiplying by the reciprocal. So we take our numerator and we multiply it by the denominator's reciprocal.
Okay.
If x was in the numerator, then we would have to flip-flop. Hi. Thank you. Sorry, I couldn't find the name. Okay, so are we good with sine of x over x going to 1? Okay, so now when we plug in 0, we get 1 over 1, which is 1. Because the cosine of 0 is 1. Cosine of 0 is 1.
Oh.
What is it? From the get-go, you just knew it? I like that. But you, I do need the correct word with your answer.
Will they do that every time though? Is that special?
As x approaches 0?
Yeah.
You're right. It will be that every time. But if I asked you that on a test, I would want to see it. Okay. Those 2 are the 2 that I want to just keep as like the memorizing, and we'll show the work for the rest. Okay. I like your thinking. Next one, write it down. I'm using U's instead of X's, and it's going to be okay. Set you up for that, didn't I? Okay, so we're still going to get 0 over 0. So direct substitution is not going to work. However, is this close to our special limit?
Yeah.
Okay, Braden, you said yep right away. What would we need if we were to apply the special theorem?
They would have to have
Okay, our coefficients aren't equal. Okay, so this would need to have a what? A 5. Can I just multiply by 5 to the denominator?
No.
But can we multiply by 1? We can multiply by 1 because it doesn't change the value. So I'm going to multiply by 5 over 5. So we have the sine of 5u over 5u, and then there's a 5 multiplied in the numerator. So this is our special limit. It's going to go to 1. So we have 5 times 1.
Ha ha.
Okay. We have one more example. Are there any questions before we get to that one last example? Okay, here it is. What kind of tacos? Oh, not tacos. Oh, I see. Okay, now, direct substitution, does it work? No. We have sine over sine, but they have different angle values. So, what?
Nothing.
Now, some of you are thinking, can it just be 3/5? Tell me that you're thinking it.
Can it just be 3/5, Mrs. Humphrey?
We cannot simplify right now to get 3/5. We have to do some work.
Can you just multiply both top and bottom by 15?
15 probably isn't going to be quite what we need. You're on the right track because we're also going to need a theta in there, since we have thetas here. Okay, so I'm going to do one step at a time, all right? If we want this sine of 3 theta to be a part of a special limit, then its denominator would need to be what? 3 theta, okay? So I'm going to split this up to sine of 3 theta over sine of 5 theta. Can I just split it into 2 fractions like that are being multiplied? Is that okay? Okay. And so then we can multiply by 3 theta over 3 theta. I just multiplied by 1, right? Why did I do that? That limit is 1.
Whoa.
Now let's take care of the sine of 5 theta. What one value do we need to multiply?
5 theta.
Okay. So I'm going to separate this out into the 2 separate fractions. So you want a 5 theta? So we're going to have to multiply by 5 theta over 5 theta. Right? What happens here? We go to 1. These thetas cancel, and our answer is 3/5. But we had to do some work to get there.
That's what I was thinking. Gosh.
You were thinking of all this work?
I was thinking it was the
Yeah. Huh. I wonder where you got that idea. Yeah.
That is inadequate.
Okay. Your homework assignment. Do it.
Very
So I
inspirational.
did page 55, but I did probably 1172.
That should be your class your homework assignment. That does.
Also, what does this graph look like?
Oh, you told us dogs. There's the dogs that are
The dots that are far apart. Okay.
That's like a quiz bowl answer.
If you relate that to PCI,